first is the area formula, which says that if you happen to have a triangle, and you know two sides of that triangle, and the angle at which they meet, well, that should be enough to just determine the triangle. Right? If I give you this point and say, okay, go that far in that direction, this far in that direction, and then stop. That's enough information to rebuild the triangle. So you should be able to compute it. We'll get an area formula. That'll be our first one. By studying that area formula, we'll prove another rule involving triangles called the law of sines. And what this law of sines will be one of the two tools we'll use to develop this philosophy is you have a triangle. Basically, any 3 facts about the triangle are enough to determine what the triangle is. If I tell you all 3 side lengths, that determines the triangle. If I tell you this angle and that angle and that side length, that determines the triangle. There are exceptions. So, let's get started. So let's try to develop an area formula for triangles. And in order to do that, let's begin with this. Here's a right triangle. Here's a right triangle. What's its area?
1/2 base times base.
1/2 base times. That's a formula that's true for any triangle. And maybe it's particularly easy to see for right triangles, because if I double that triangle over its hypotenuse, I get a rectangle, which is easy to get. The area is exactly base times height, but this is like half that. So what about if what happens if I give you a non-right triangle? Let's suppose I give you this triangle with side lengths A, B, and C, and I happen to tell you this angle little a opposite the side B. That should be enough to determine the area. And let's see if we can do that. So the area formula says that the area is 1/2 base height. So let's start by drawing the height. I'm not allowed to have the height in my final formula. I'm only allowed to use side lengths and that angle. Those are the only things I want to use. But let's go ahead and draw this height. Let's label it H. This triangle, can you now tell me what the area of this triangle is? Yeah, it's 1/2. What's the base of the triangle? Let's see. What's behind the triangle? H, which I'm unhappy with having to use an H in my formula, but if I can get rid of the H, then I will be happy. 1/2 times C times H. Now, let's look at that. If I could get H in terms of the other symbols in this picture, that would make me happy. And I could just substitute in that value for H and be done. So let's take a look at just this piece of that triangle. Is that a right triangle that I just shaded in? Cool. Do I know an angle of that triangle and say one side length? That's enough information to determine that triangle. I know the angle A. What side length of that triangle, that green triangle, do I know? Well, the thing is I don't know H. I would like to know H. But I know B, so I know its hypotenuse. So here's this little triangle. A. I don't know how big the base is because this whole side length is C. I don't know where this point lands right now. I would like to know H, but I know the side length C. I'm given that as part of the data of the formula. So what trig function should I use if I want to know H? Sine seems promising. So by SOHCAHTOA, I see that sine of A is opposite H over hypotenuse, C. So, what's H? Is the light green too faint?
Oh, this one's B. Oh, oops. Thank you. So I guess that means the sine of A is equal to H over B.
Which is still an equation you could solve for H, right? Multiply both sides by B.
H is equal to B times the sine of A. Nice. So that means I know what H is. So I can take the H in the area formula
And substitute this value. If you do that,
well, what you'll get? You'll see that the area of this triangle is 1/2 times C times B times the sine of the angle A.
there's the area formula for triangles. If I know two angles, two sides of a triangle, and the angle at which they meet, then I can compute the area of the triangle
As 1/2 side, I'm going to put them in more reasonable order, times side times the sine of the angle at which they meet. So if B and C are sides of a triangle, which meet at an angle A, then the area of the whole triangle is 1/2
B times C times the sine of A. So there's a formula. Let's use it to compute some stuff. Here's a triangle.
It has a side length 2, a side length 4, and they meet at an angle of pi over 8.
So what's the area of that triangle?
Or sine pi over 8.
Yeah, so I guess you've done some simplification already. So 1/2 times 2 times 4 times the sine of pi over 8 is the area, which, as you know to simplify, is to 4 times the sine of pi over 8.
So way back when, we didn't justify why the sine of pi over 8 should be some particular value. We will next week. Does anyone remember just what we stated that it was equal to? That's an unreasonable thing for me to expect you to remember. A single obscure fact from a single lecture that hasn't reappeared since.
The sine of pi over 8 is the square root of 2 minus the square root of 2 all over 2. So this simplifies a little bit to 2 times the square root of 2 minus root 2.
And, well, I don't know, as soon as you got down to sine, 4 times the sine of pi over 8, how many people took out a calculator and computed it? Tell me, what is this approximately equal to?
Oh, should I? No, that's fine.
What is this area approximately?
Like a decimal approximation?
Yeah.
1.53.
Cool.
People feel pretty good about this area formula? It's a formula that gives you the area of a triangle. I suggest you just internalize it, but why is it true? It's true because you know the area is 1/2 base times height, and you can compute the height of any triangle using trigonometry.
So, as a consequence, we'll get a rule called the law of sines.
And here's how we'll get it. So let's suppose I give you all of the sides and all of the angles of this triangle. Well, do you know at least two sides of that triangle and the angle at which they meet? In fact, you know any two sides of that triangle and the angle at which those two sides meet. That gives you three different area formulas.
You know that the area should be 1/2 B times C times the sine of A. It's very intentional here that each of the angle labels is the same letter as the side opposite. Right, the names aren't important, but the formula will be the most beautiful if you use that sort of naming system. Is there another pair of sides that you could use the area formula at?
A and B.
A and B. You know that the area is also 1/2 A times B times the sine of the other letter, C. Is there another pair of sides that you know the angle at which they meet?
A and C.
A and C. And each of those should give the area of the triangle. But the area of the triangle is just what the area of the triangle is. All of those quantities should be the same. Do you think I could say set two of those things equal to each other, do some algebra and simplify and get some equation out of it? Let's do it. Let's take the first two. So here's what I'm going to do. I'm going to do one of them here. Then I'll let you guys pick a remaining one, and you'll do the other one. That'll give us all the information that we need for the law of sines. So let's do this. Let's take the first two. So I know for a fact that 1/2 B times C times the sine of little a should be the same as 1/2 A times B times the sine of little c.
So let's look at that equation and try to simplify it. Do you see anything that cancels? Do you see any of the same thing on each side of the equal sign?
1/2 and B.
There's a 1/2 on each side and there's a b on both sides. So by canceling the 1/2 times b from both sides, I guess that means you're dividing it from both sides in this case, but that's okay. You'll see that c times the sine of a is equal to a times the sine of c.
And in order to distinguish my capital C from my little c, I like to draw my middle c's like their title names. So, here's the game. We'll get a formula that'll be nice looking if we sort it alphabetically. So all the A's are on one side and all the C's are on one side. So what should we divide both sides of this by?
Sine of A and sine of C.
Sine of A, sine of C.
And what will we wind up with? We'll wind up with big C divided by sine of little c is equal to big A divided by the sine of little a. There's what the law of sines says. The law of sines says that, I'm going to try to put these in alphabetical order, a divided by the sine of little a is the same thing as c divided by the sine of little c. Now, what do you think is going to, can you infer by recognizing a pattern what should go in that middle blank? Probably b divided by the sine of big B. And now maybe I'll give you guys an option. How many of you would like to go through the algebra again and see how to get the b over the sine of b to show up in the formula? Okay. You all have a pretty good idea how it's going to go because it'll be almost the same ones as there are to the left, but to the right. So there's the law of sines. The law of sines says that if you start with a triangle with known side lengths A, B, and C, and angles, little a, little b, little c, opposite those side lengths, we get the equality that any side length divided by the sine of the angle opposite is the same as all the rest. Let's use that. Let's do something with that. Here's a triangle. It has a side of length 2 each, two known angles, one of length pi over 6 and another of length pi over 4, and I don't know any of the other facts about this triangle. Let's try to figure out some other facts about that triangle. Now, the law of sines gets really useful as soon as you know the measure of an angle and the length of a side opposite, because then you'll know one of these things. In this picture, though, is there a pair consisting of an angle and a side opposite that you know?
No.
No, but is there almost? What do the interior angles of the triangle have to add up to? 180 degrees, following a radians? Pi radians.
So I know these three angles have to add up to pi radians. So I know that c plus pi over 6 plus pi over 4 must add up to pi.
Do you think you could solve that for C? I mean, of course you can, right? You just need to subtract two things, and then maybe do some simplification.
Doing that, what do you get for c?
7 pi over 12 I hear?
Cool, so now we know the side length c is 7 pi over 12.
Now do we know a pair consisting of an angle and a side opposite? We know 7 pi over 12 is opposite the side length 2e.
So let's use that to set up some equations. So that means we know that the sine of 7 pi over 12 divided by the length of the side opposite, 3, is the same as a divided by, nope. So I'm using the reciprocal of the sine law, which is equivalent, but I'll stick with what's actually written above. So I know that I know that this side length divided by that angle, 3 divided by the sine of 7 pi over 12, is the same thing as a pair consisting of any other side length and the angle opposite.
So I think I'll go through the walk of either solving for A or solving for B, and maybe leave the other one to you guys. Would people rather have me discover the side length A or the side length B? A? Who? B? No. Okay.
Fair enough. The alphabet goes in a particular order.
So I get this equality. If you wanted to solve that for A, what would you do? I guess multiply both sides by the thing in that denominator, the sine of pi over 6. Quick reminder though, what's the sine of pi over 6? Because that's like a thing that you know, right? That number that's in the unit circle? It's a half.
So let's multiply both sides of this equation by a half. So doing that, we get a equal to 3 times 1/2 divided by the sine of 7 pi over 12. And I guess the only simplification that one can make is putting that 2 in the denominator, because I don't know what the sine of 7 pi over 12 is. We will once we know the half angle again. So there's an exact value for A. Let's approximate. Let's determine approximately what 3 divided by 2 times the sine of 7 pi over 12 is. Divided by 2 times the sine of 7 times pi over 12. Unable to connect. Okay, well, that resolves that. I won't be doing any computations myself. Well, that's because I'm not actually doing a Google search. Silly me. Chris. Of course, at this point I'm totally flustered and so probably made a typo. Oh, I didn't know that Google would do graphing for you. I guess it does.
Somewhere around 1.55? Does that agree with the other people who did the computationally fast forgot? Cool.
So in general, as I kind of pointed out, if you know 3 things about a triangle, generally speaking, you know the other 3 things about this triangle. I guess one exception is if I tell you all 3 angles of the triangle, is that enough to determine the triangle? Because you could just like scale up that same triangle with all the angles and the sides are totally 3 to be however big they are. So the 3 angles won't cut it. But generally, if you know any other 3 facts, you can figure out the triangle, and let's walk through it. So whenever you know 2 angles in one side, well, we just did this example, right? If I give you a triangle where you know this, and you know this, and you know that, the first thing to do is determine that third angle. And next, use the law of sines to get the remaining sides.
We're going to feel pretty okay?
If you're in a situation where you know, where you have a side angle side triangle, that is a triangle where you know 2 side lengths and the angle at which they meet, well, then you're in a situation where you really should use the law of cosines, not the law of sines, which is a rule that we'll develop on Monday. If you have a situation where you know 2 consecutive sides and then the angle opposite, it turns out you're in an ambiguous case. And maybe before we see that it's ambiguous by doing a specific example, let's see why it's an ambiguous case. Let's suppose I tell you a side length, an angle of the triangle, and some other side length. So I don't know what angle this side length could come out of. But let's see that there could be 2 solutions. So let's see, I have no idea how big this angle, I know how big this angle is, I have no idea how long that side length is then. Well, let's see, I'm going to do my best to draw a circle centered there. It's a circle. Well, so I see 2 different triangles. So I see this triangle, and I see this bigger yellow triangle. Nope, bigger yellow triangle. Do those both have this side length? And they both have that side length the same, and they both have this fixed angle. So both of these 2 different triangles satisfy the side-side angle information that we've given. So in general, there will be 2 solutions, but 2 isn't that many. Let's go through the walk of determining those 2 solutions in one particular example. So here's a triangle. Let's suppose I tell you that there's an angle of length pi over 6, which is opposite a side length of the square root of 3, and next to a side length of 2. Let's try to determine the remaining information about this triangle. And let's, right, we have a new hammer, a law of sines. Let's try to get this hammer. Do you know if they're consisting of an angle and a side length opposite? I think you do. Is there an angle you would like to know, which is opposite a side length you do know? That's what you need. So you know that the square root of 3 divided by the sine of pi over 6 is equal to 2 divided by the sine of little c.
How many unknowns are there in that equality? 1. One equation, 1 unknown, we can determine c. And how are we going to do that? I guess you should multiply both sides by sine of c, multiply both sides by the sine of pi over 6, divide both sides by the square root of 3.
And what will you wind up with? You wind up with the sine of c is equal to 2 times the sine of pi over 6 divided by square root 3.
And I guess before we move on, does that simplify it off? What's the sine of pi over 6? I feel like all the angles I said today are pi over 6. It's a half, right?
Yep.
2 times a half is 1. So I get the sine of this angle C is 1 over root 3, also known as root 3 over 3.
Now see, what's the biggest angle you can ever see as an interior angle in a triangle? Yeah, like a tiny bit less than 180. So 179 isn't even bigger. You can go a little bit bigger than that. You can get any angle that's strictly less than pi radians. So,
How many angles between 0 and pi radians, I guess excluding 0 and pi radians, you can't have a triangle with an angle of 0, you can't have a triangle with an angle of 180 degrees, have that as the sine of c? That is, tell me what are the solutions to the sine of c equal to root 3 over 3?
hey, is that like a trig equation? A simple trig equation? Yeah, so this is like the one that we have the solutions to by using that flowchart. But we don't want all the solutions, we just want the ones between 0 and pi. So what's the elementary solution to that?
So we can inverse sine of root 3 over 3.
C equals inverse sine. I'm going to use the Google calculator, and the Google calculator uses the terminology arcsine, so I'm going to use the word arcsine. If you like the word inverse sine, go for it.
Cool. And in the graph of sine, that gives us like that solution. Is there another solution to this equation between 0 and pi? Yeah. Nope, that's too big. Plus 2 pi would be like over here. Yeah. So I'm going to draw this picture. That's a perfect unifocal with that and its center. So here's the angle that you just found. How do you describe this angle? Pi minus that other angle. So here's the other angle. So, how many choices of C might there be? Now, it won't always follow that both of them will be valid choices of C. It won't always follow that they'll both be different. But in order to see that there are two solutions to this triangle problem given, let's try to determine the side length little a. And then we'll use a calculator to compute everything to make sure that all of the angles are actually valid. If we wind up with A being like a negative angle or something stupid, then we'll know that that's not a valid choice for A. So, tell me, so in each of these cases, we'll know what C is. C is one of those two things. For each of those two things, could we determine the angle little a? Yeah. So either A will be pi minus pi over 6 minus the inverse sine of root 3 over 3, or A will be equal to pi minus pi over 6 minus the other option for A. And I guess that's the same thing as arcsine root 3 over 3 minus pi over 6.
So there are two options for A.
Let's take a moment and just determine if they're both even valid options by getting decimal approximations. So let's cross as soon as I wanted the computer the screen shut off. So pi minus pi over 6, that's 5 pi over 6, even if it's not written, we know that. 5 pi over 6 minus the inverse sine of the square root of 3 divided by 50. And the thing is that I did actually check that, and I knew that that wasn't going to walk. I should have known that that wasn't going to walk. Can't show history. Will you let me paste? So I get a decimal approximation of somewhere around 2 radians. Is that a valid angle? Is 2 less than pi? So that's a reasonable angle.
So one of our options is somewhere around 2.003 radians, which you could convert to degrees if you wanted to. The other possible option is the inverse sine of root 3 over 3 minus pi over 6. Which is somewhere around 0.0092. How do people feel about that? Oh, yeah, you want to see what I wrote. All I did is I wrote those numbers. Oh, I wrote 1 next to 0? Okay. Well, that's because I just meant the decimal place to be there. Do you feel pretty good? So let's close with some applications. Right? All of this maybe felt a little bit abstract, and maybe even a little bit wrong. So let's try to come up with some applications where you can use the trigonometry to model real-world problems and address things. And the philosophy behind the first is the idea of triangulation. If you have two different viewpoints, two different people watching something, you know the distance between those two people, and you know the angle that they're looking, you can figure out the exact location of the finger. And what you need to make that happen is trigonometry. Let's see it happen. So, you and Katrina Allen who happens to be the current top-ranked US PDGA player, are standing in the field and see a flying saucer pass overhead, as should be absolutely not surprising given the context. You're standing precisely 40 feet apart, and as the flying saucer passes over you, each of you records the deviation of the angle from you to the flying saucer to the horizontal. You record the information in this picture. That should be enough information to determine any fact you want to know. You should be able to determine exactly where the flying saucer is. So let's try to answer, I guess, 3 questions. What's the distance from you to the flying saucer, from Katrina Allen to the flying saucer, and how far above the ground is that flying saucer? So let's go ahead and do it. So maybe So let's label all the sides I want. I want to know how big is that side length, because that's the distance from you to the flying saucer. The distance from Katrina Allen to the flying saucer. And I would also like to know how far the flying saucer is above the ground. That is, I would like to know this side length.
I think I'll give you guys a choice. I can keep talking, or you guys can just do the computation and we can come together in a little bit. People want me to keep talking? Cool. Then I will keep talking. If you want to go through the computation on your own, you will finish before I finish. So, let's see. By looking at that 2 pages ago thing where I said what to do if you know an angle aside and an angle. What's the first thing we should do? Determine the unknown angle. What do 3 angles of a triangle add up to? 180 degrees. And this time degrees is appropriate because everything else is given in degrees.
So let's try to determine this angle. So I guess this angle, I'll call it question mark, should be the same as 180 degrees minus 85 degrees minus 70 degrees. So let's see, 180 minus 70, that should be like 110. Will it wind up being 25 degrees? I think it's 25 degrees. All right, good. So this angle is 25 degrees.
Do I now know a pair consisting of an angle of the triangle together with a side length opposite? Yeah, so that's exactly what you need to use the law of sines.
So I know for a fact that the side length opposite, 30, divided by the sine of 25 degrees is the same thing as A, maybe I'll try to find A first, divided by the sine of 70 degrees. Because A is opposite the side length 70.
Is that not to solve for A? Of course it is.
And let's do both. Let's get an exact value for A and get an approximation. A is exactly equal to 30 times the sine of 70 degrees divided by the sine of 25 degrees.
And on the one hand, like, that's a number, that's a final answer. But maybe we actually care about how big this number is. We have reason to care about its decimal approximation, so let's approximate it.
That will be 30 times the sine of 70 degrees divided by the sine of 25 degrees. Get something like 66.7 degrees.
How do people feel about that? No, it's not. That's not in degrees, is it?
It's not an angle, it's a side length. It's in feet. There we go, that's better.
Nice. So, just in order to save myself time, how many people have themselves, at this point, computed the side length feet?
B is approximately 77.3. 0.72. Okay, so I'm going to just go to that many decimal places. I'm mishearing you entirely.
70.7. Okay.
Sorry, listening is difficult. So that's an approximate answer. What did you get for the exact value? Something that looked about like this.
30 sine 85 over sine 25.
Cool.
So there's how to compute the side lengths A and B. But there's one other thing that's asked. How far above the ground is the flying saucer? Let's try to compute that. And in order to do that,
Well, maybe one strategy is, do I see a right triangle
for which I know at least one angle and at least one side for which the height is another side of the right triangle? Yeah, I guess it's either that one or the other one.
take your pick, they both better give the same answer. So let's do that. So there's the height. I know that that side length is A. I have a value for A, but it's too long to write, so I'm not going to write it. And I know this angle is 85 degrees.
Which trig function seems useful here? I would like to know the side length opposite 85 degrees. And I know the hypotenuse, so sine.
So the sine of 85 degrees is precisely the height, which I would like to know, divided by a. So let's just
Multiply both sides by a without even writing that first equation.
So what can I say? I can now say the height is,
So what you might be tempted to do is say, well, I know that a is like somewhere around 66.7 feet, and I can then multiply that by the sine of 85 degrees. That'll give you an approximation, but I wouldn't be totally confident in even that false decimal place because you're going to have rounding errors probably.
so instead, what I'll say is write down the exact value. The height is a, which is 30 times the sine of 70 degrees, divided by the sine of 25 degrees, then that multiplied by the sine of 85 degrees.
Because you see, now you haven't forgotten any information. You haven't done any rounding until this last step. The computer will save way more decimal places than you'll write down on the page anyway. And well, now if you wanted to compute that, you have a machine. You can plug that in. The only reason I won't is because I have 15 seconds left and I don't type that fast. Nice. So as people are leaving, everyone should have notes from today, a review for the midterm, which is to be collecting the points back, and a sample for the midterm, which is not to be collecting the points back, but which I will post solutions to. Both of the latter two documents, a revision has already been made to the online volume. A problem has been added. So make sure to take a look at the online volume from the webpage, which will have the solutions for. Thank you.
I'm not so confident, but that's also my fault.
They both have a very similar additional problem. You survived.
I would just like bring it completed and show you before I left class. Are you able to check me out?
Oh, before I do that.
Like I don't know if I can run up here.
That's a little bit tight because there's lots of tools on my head. I'm available most times on Monday, and I might even be adding an office hour on Tuesday, but I do have some available time on Tuesday.
Okay.
So it started like 1 o'clock.
I'm available most anytime on Tuesday. I'm planning on starting an office hour. What time is your favorite hour on Tuesday?
Usually that way.
I can come in.
Are you here this weekend?
Well, Monday I'm free at 2.
I'm available at 2.
Okay, can I go to your office hours at 2 on Monday?
Yeah, there will be office hours, but you can come back.
You'll be in your office.
Yeah. And if you even just, if you want to, if you have any specific questions over the weekend work lesson, you can send me any specific questions.
Okay.
And solutions to the sample documents will be posted probably by Saturday.
Okay, but you'll be in your office at 2 p.m. on Monday?
Yeah.
Okay, thank you.
Yeah.
I am even worried about like
Yeah.
I'll just pop by.
Yeah.